Hello everybody to our tinyML talk, AutoFlow, an open source framework to automatically implement neural networks on embedded devices. Yeah, we from the tinyML Foundation want to thank every of our strategy partners. So our strategy partners are RON devices, DeepLight, EdgeImpulse, EMSA, PhotoHub, GreenWaves, Gravity, HOTG, ImageBob, Ementris, Clarkatech, Latent AI, Maxim Integrated Analog Devices, Micro AI, NXP, Profis, Qualcomm, Quexo, Reality AI, Winisys, Wixine, SAP, Seed, ZenCML, Sony Semiconductors, ST Microelectronics, Stream Analyze, SynSense, and Syntium. Thank you very much for your partnership. If you're interested to be a partner also, please contact Olga at tinyml.org for more information. We are really thankful that we can hold our tinyML Summit this year. It was a really successful meeting with 300 attendees and a really successful research symposium. If you're interested in the Holden talks, you can rewatch the talks on YouTube or have all the information on our homepage, tinyml.org. Our next tinyML trailer play series will be with Eric Pan, the founder of Seed Studio, and it will be on the 6th April at AM Pacific time. If you're interested in tinyML or embedded machine learning, please join our group and Meetup, or please join our tinyML community on LinkedIn. If you're interested in more information or other talks or old talks, you can subscribe our YouTube channel, our tinyML YouTube channel, and get more updates about the tinyML field and learn about our videos. Our next tinyML talk will be on Thursday, the 7th April, from Lucas, the CTO of Contact.io, and David, he's the R&D leader from Contact.io. The talk will be about battery optimization, people counting using FER and AI. The webcast starts at 7 AM Pacific time. If you have an interesting topic or you want to make a talk in the field of AI or tinyML, you can contact us at talks@tinyml.org for more information. Let's go to the topic for today. I want to present you Daniel Konegen. He studied mechanical engineering and mechatronics at the University of Furtwangen. In his master thesis, he worked on the automated implementation of neural networks and embedded systems. And after he completing his master's degree, he's worked as a researcher for the tinyML field. The second presenter will be myself. I studied electrical engineering at the University of Furtwangen, and since 4 years I worked at the Hahn-Schickard Research Institute as a researcher in the field of tinyML, and I'm currently doing my PhD at the Technical University of Munich. So now, Daniel, the stage is yours.
So hello also from my side. Like Mark said, I'm Daniel. I'm researcher at Hahn-Schickard. And I'm responsible for the areas of embedded AI and data science. A few words to Hahn-Schickard. Hahn-Schickard is a research institute for microelectronics. We have 4 locations in Germany, and since 2017 we have an AI group with currently 9 members. So now I want to tell something about our tool AutoFlow, where you can bring your AI to the edge. And like Marcus said, the developers were Marcus and me. So now I come to the agenda of our presentation. First, we want to talk something about what is AutoFlow and why do we need it. The second part would be how does AutoFlow work. Then we start with which features are included in AutoFlow. Then I give a short demonstration of the tool, how it looks like and how you can use it. Next, we explain how you can use it, what you have to do to use it, for example, the installation. And the last part of the presentation would be how can you take part in the development of AutoFlow.
So yeah, let's begin with the topic, what is AutoFlow and why do we need it? So everybody of you who designed a neural network or make his own machine learning model know that it's not that easy to implement the model on embedded devices. So it's not that easy that you can take your model, TensorFlow model, and yeah, execute it on the embedded device. In between, there are some manual steps you need to do. For example, optimize the model or yeah, convert it for TensorFlow Lite. And this so this handle up the first problem. So data scientists or yeah, tinyML engineers need knowledge in 3 areas. So we have the machine learning area, so how to build a model with the given data. Then we need knowledge of embedded systems, and we need knowledge of the data itself. So the domain, we need to be an expert in the domain, or need the basic understanding of the domain. And so this is because this to bring everything in one person is hard. We written AutoFlow, which helps the developer in every point in the development of a tinyML system. So in general, we can say AutoFlow automates the whole process, the development process, so it's easy and fast. So it enables easy and fast use of tinyML. It covers really the whole workflow. So the normal workflow for an embedded system, or to bring AI on an embedded system is here given in the image. So we have we want to train a model with, for example, TensorFlow. Then we have to select a target. Is this a microcontroller? Is this an FPGA or a single board computer like an Raspberry Pi? Afterwards, we can prune it or quantize it for the target platform. Then we make a conversion, or we convert it in, for example, .c or .h file for microcontrollers, or an VHDL file for example, FPGAs. And afterwards, we can compile the model for the embedded device. And yeah, with AutoFlow, we want to give help on really every point. So from train the model up to the conversation in the model. AutoFlow contains 2 parts. So we, on the one side, we have the optimization and implication of neural networks for different target platforms, and on the other side, we have the optimization generation for neural networks for embedded devices. Yes, so the first side is the optimized generation of neural networks for embedded devices. So in the back end, we use AutoKeras. AutoKeras is a really cool framework which helped us to put data into AutoKeras, and then it built a model with auto machine learning for the data. And yeah, so we implement this great framework in our tool, so that we only can select data from different data targets. For example, we can load whole folders with the data inside the folders, or we can upload, or we can put some CSV files, or we can write our own data loader script in Python and only load the data folder script. Then we can, for example, select what we want to solve or what the problem is about. For example, if we have an image classification or regression, or does we have normal data or time series data, and yeah, is the classification or a regression task. Afterwards, yeah, we can start the model search process, and then we get the best model for the data. Yeah, the second part about AutoFlow is optimization and implementation of neural networks for different target platforms. So the first step is to select the model. And on this point, it doesn't care if you trained your model by hand on, for example, TensorFlow, or is it trained automatically from AutoKeras. Then we need to put some, there's the need to put some general information about the project, so the project name and the output path of the generated files. Then we can choose a target platform, for example, microcontrollers, FPGA, or one platin computer, one board computer like Raspberry Pi or NVIDIA Jetson. After we select our target, we can select some optimization algorithm, for example, pruning or quantization, but this step is really optional, so we does not have to optimize the model, but if we do, we need to give some trainings data again to the tool that we can retrain the model after we prune it or after we quantize it. And after some clicks, we can start the process, and then the model gets automatically implemented on the embedded devices. So now Daniel will tell us a little bit about pruning and quantization.
Yes, like Marcus said, we implemented two optimization algorithms. One is pruning. Pruning is for to remove redundant weights of the model, which are not needed to for the model. And the goal of it is to reduce the model size, the memory size, and this should be done by minimal loss of accuracy of the model. So on the left-hand side, we have the model before pruning. We have 4 layers of the model, and each layer is a dense layer, and every neuron is connected to the neuron of the next layer. And TensorFlow has already implemented unstructured pruning. You can see it in the middle, but the bad thing about it is that they just prune the weights of the network, and you don't prune the neurons by itself. And by pruning the weights, they just set the values to 0. And the bad thing about this is that you have to store the weights, and you don't lose any memory. So our approach is the structured pruning. We prune whole neurons of the different layers, so that we, for example, here in this example on the right side, we have pruned 2 neurons in the first layer and 1 in the second hidden layer, and because of this we save the space of these neurons and of these weights. Our implementation is in 2 different versions. The first version is with factors, that we define specific factors for pruning. We implemented pruning for dense and convolution layers. And with these factors, we say how many % of the neurons or filters should be deleted by in each of these layers. And after we specified the prune factor, the neurons and filters get removed. And after we remove the neurons and filters, we have to retrain the model to gain the good accuracy again. The second version is the pruning for accuracy. There we can also choose 2 different ways. The one way is to define a minimal accuracy, which should be reached after pruning. And the second one is the maximum loss of accuracy we gain. So this works like this. We remove neurons and filters and start with a factor of 5%. And after this, we retrain the model and look if we can reach the accuracy which is defined on top of the top things. And if we reach the accuracy, we increase the factors, and after this, we retrain the model again, and we repeat this step until we don't reach the accuracy we want to reach. So the second optimization algorithm is the quantization. So quantization reduces the number of bits we needed to represent the value of the weights of the model. And yes, also, this is also the goal of it, is to reduce the memory space of the model. And normally you see the weights of the neural networks are represented as 30-bit float values. And in this case, we want to change them, to quantize them to integer 8-bit values. So on the image at the bottom, you can see a little example for this. You see a sine wave. The left image is the original signal with a lot of different values. And yeah, for every value is stored as 30-bit float value. And the right image shows the quantized model, where the where the values are quantized to values of 8-bit integer values. And yeah, you see you don't have that much different values you have to store. So, and also for this, for quantization, we have two different versions. The first version is integer 8 with float 32 fallback. So in this case, we have we quantize the model weights to 8-bit integer values, but the model input and the model output are still 32-bit float values. The other implementation is the integer 8 only version, where we have also the model weights and the model input and model output all as 8-bit integer values. So now which features are included in AutoFlow? So first we have to say AutoFlow is based on TensorFlow, and we have an automatized generation, optimization and conversion, and this is only possible with TensorFlow models. And the main features of AutoFlow are we have a graphical user interface, and this makes it easy to get started with tinyML. You just can do it with a few clicks. And we use AutoML, like Marcus said, we use AutoKeras. And with this technique, you don't need a lot, or you don't need any knowledge about machine learning, and you can create your own machine learning models. We have an automatic compression, like I told, with pruning and quantization, that you can reduce the memory of your machine learning models. Then we have automatic code generation for the different target platform which you want to select. So for microcontrollers, FPGA, and single board computers. And like I said, we use various target platforms that the machine learning models can be executed on: microcontrollers, FPGAs, Raspberry Pis, and so on. So now I have a little demonstration of our tool, how it looks like, how the GUI looks like, and how it works. So now we start at the beginning. We can choose if we want to train the model using AutoKeras, or if we want to load an already trained model by ourselves. So we start here by train a new model with AutoKeras. And in the first window, we have to type some input data, like the model name, how it should be named. Yes. Then we choose the target folder where the model should be stored, and then we can select our data. And here I will pause short, and you can see you can transfer the data in different ways. Like Marcus also said before, on the one hand, you can pass a folder which contains images with different classes. Or you can pass a CSV file where the data is stored, or you can pass a Python script where also you can define your data loader, how the data is loaded, and you have to return the data for training and testing later. So let's go on. So in this case, we choose a CSV file with some data we want to train our model. So if we choose a CSV file, we see this little window where the data is previewed. You can choose the separator, how the data is separated. You can choose which kind of decimals you use, if you use a point or a comma. And then you also have to define in your CSV file where your label of the data is. In this case, we have in the first column our label of the data. And yeah, if you click preview, you see here your data. And yes, you also see the total rows and total columns. So then you can go next and you define your task you want to choose. In this case, we want to do a data classification. And in this window, you can define how many, first, you can define how many epochs you want to train your model. Second, you can define how many different models you want to train. And the last part is the maximum size which the model should have. And if you just take a 0, you say, okay, it doesn't matter which size the model have. So in this case, we say, okay, we want to train 50 epochs and we want to train 10 different models. And we ask if you want to start the model training. Then we are in this window. Then there will be 10 different models will be trained automatically and each 50 epochs. And after these 10 trials, the best model is stored in the output path you defined before. And yeah, until then you are here in this screen. And when it's finished, you get back to this window where you can convert it to the platform you want to. So here in this window, you also select the model you trained. You see it here in this folder. The model name, the project name, and the output path is like you said before. And in the next window, you define the target you want to execute the model, if you want to do it on an MCU, FPGA, or SBC. And in this case, we want to use an MCU. And here in this window, you can choose the optimization you want to use. With a few buttons you can select here. If you want to use pruning or quantization, you don't need to do it, but here we want to do a pruning and we want to use the accuracy pruning, and we just want a loss of 3% of our model. And for quantization, we say, okay, we just want to use integer 8 data, integer 8 only data. And the thing is here to say that we just use unsigned integer 8 data. This is also important to recognize. And after it, you need to specify some training data to retrain the model. And because we trained our model with AutoKeras, the data path is already selected. So we don't need to do here something more. And at the end window, we just have to define for the microcontroller how much space we want to save for the model on our microcontroller. And we get here a little summary of our project, like name, the output path, that we can check if everything is correct. And if everything is correct, we just click next and the project gets created. Then we have here this little loading screen again, and we have to wait a little bit. First, the model gets pruned like we defined. After it, the model gets quantized. And in the last step, the model gets converted to TF Lite, and after it to a C++ model, and all the necessary files get created. So then the next thing is we just look on these files here. We see, okay, our target, our project folder is created, and we see, okay, we have here our pruned model first, our TensorFlow Lite model. The TensorFlow library, which is needed for the microcontroller, is inside here. We have a source directory with all our source data, yes. For the first one is the the data or the script to load the model, read the input data and execute the model. The second one is the C++ model. And we have some header files for, which are defined as source files. So yes, this was the little demonstration of our tool. So go next. How can you use the tool? First, you can use the tool just by downloading it from GitHub, because it's an open source tool, just with the command git clone. You can download it. After it, you need to install some requirements, which are defined in the requirements.txt file. You just can install them with one simple command with the pip install. And the last one is to customize AutoKeras a little bit, that you can execute the AutoKeras models on your target device. So, and now the question is, how can you take part in the development of AutoFlow? As we mentioned before, AutoFlow is an open source tool and can be found on GitHub. I showed the link before. And yeah, there you can maybe post some new issues with content like what are new features which should be implemented, which you think would be wonderful to see on AutoFlow, or what should be changed in the code, or yes, maybe also some code changes, or what is not working, if there are any errors or warnings or something like this. And you're also welcome to implement your new functions and features by yourself and create a pull request and send it back. And if it fits to our vision of AutoFlow, we will be very happy to implement your changes or your new features. So now I show you the GitHub page. It's like this. In the README file, we were very interested to make it quite nice to see and to look, and that you get a lot of information of our tool, and also, for example, the installation, that you know how you have to use it, for example, in Windows and in Linux. And if you want to make some changes in code, for example, we also showed a little GUI flowchart, which file depends on which file, or from which file you go to which file. And we also have a little getting started, with also the explanations I had here in the demonstration. For example, also the training of new models with AutoKeras, and also if you want to use MCU and FPGA or a single board computer, what you have to do, the different steps of it, and yes, also a little other things like what features we want to implement in the next time. For example, to release it as a toolkit, that you also can use it without the GUI. Yes, like this. So now it's your turn, Marcus, again.
Thank you very much, Daniel, for the demonstration and all the other information. So yeah, now we are more or less at the end of the presentation. Here's some small additional for the German attendees of this talk. If you're a German SME and are interested in AI, we can give you a free offer for SMEs. So we can offer small trainings for you and your company, or we can pronounce some AI events or trainings, or we can make some small application studies. So we can, for example, if you have data and you want to try if this is possible with AI, we can help you with this. And every of these points are fully free, and don't hesitate to contact us. So in the this is the last slide for this presentation. To summarize everything, we can say, this is an open source tool, AutoFlow. it should be easy to bring AI in embedded systems as easy as possible. And if you're a developer and are you interested in bring some new features, or if you have feature ideas, yeah, please write it on the Git, or maybe program it yourself and use the pull request button to use it, to publish it. It would be cool if we can build a small community around this tool, that we develop together this tool more and more further. And yeah, I think we can bring together our knowledge and our work time, that we bring something cool out together. So yes, now we have a small 5-question pool. Please answer this, and afterwards you can ask question in the Q&A window. So yeah, so we start with the questions. Some of them I answer, some of them Daniel will answer. So the first question is, what is the minimum possible number of bits after quantization, Daniel?
Yes, now. So sorry. So the minimum possible number of bits after quantization are 8-bit. So 8-bit integer.
Okay, thank you very much. So then the next question, AutoFlow performs all trainings calculations on local machine or on cloud. Is cloud also possible? In the moment, cloud is not possible, but yeah, like, so everything is local. This is more or less the reason why we developed this tool, because that there is no need to send your data on a cloud. For example, when it's really privacy data, or yeah, when you want to stay your data local on your computer, then yeah, this tool is pretty fine for you, because nothing is sent out and everything is working local. But if you're interested to make this tool on the cloud also, then yeah, don't hesitate to use this code. It's open source. Write your code, your extension on this. It would be cool to use it on local or on the cloud. So Daniel, the next question for you is the model memory. Is this on the flash or on the RAM, or what does the model maximum size mean?
So it's for the RAM. So the bigger problem, like I understand, is for the RAM. Yeah, that the model execution is, for example, the convolution layers are more, you need no more calculating power, and yeah, it's stored at the RAM, and that's the bigger problem of it.
Okay, great, thank you. Then, oh, there come on more questions. So the next question is, does it support LSTMs for FPGA? So in the moment, not, because when we start, the HLS4ML doesn't support any LSTMs, but now it does. So we're working on it too, that we can support LSTMs. Or like I already told, maybe you're faster than us, then you can write the you can extend our code and make LSTMs possible for FPGAs. Thank you very much for this question. So then the next question is, are there constraints, for example, accuracy or size, are there hard constraints, or is it always possible for the tool to find the solution? And thus we have compared the quality of the output solutions with other state-of-the-art models. So yeah, for this question, so the constraints are hard constraints. So maybe you need to try a little bit around what is the best solution, or what is a good solution. The model find always a solution, but yeah, it depends how good it is. So if you say the model must be really that small, then of course the model can't find a good solution. Then to the second question with the state of the art. So AutoKeras, there are a lot of paper from AutoKeras how good it is and how good in case of state of the art it is. There are a lot of works you can read about this. But there is so you don't need to use our training or the AutoKeras training. So you can use your model you want. So if you have a state-of-the-art model, then you can use it also. So there's no problem with it that you use state-of-the-art models. So yeah, then the last question for, or the last question for you, Daniel, is the one-time code also generated from the tool?
Oh, sorry, I didn't ask. Which tool we use? We use PyQt to design the GUI. Yes.
Okay, thank you. This was not directly the question, but so yeah, we use PyQt to develop the GUI. But the other question was, is the one-time code also generated from the tool? Yes, the one-time code is also generated. So you have one file with the model, for example, the TensorFlow Lite model, and one file where you can only put in your code that you can execute it right directly. So you don't have to find out how to use this model. This should be no problem also. And then the last question, which machine learning frameworks are supported in the moment, only TensorFlow and Keras. And now I repeat myself, but if you're interested that we should support more features, you can write this as an issue, or you can program it yourself with the development documentation. And that should be pretty easy for you when you work with PyTorch, that you, yeah, for example, PyTorch, that you can make everything works for PyTorch. Yes, good. Thank you very much. So, okay, there's one more question popping up. Could you provide a few examples of commercial deployments? So it doesn't do this tool commercial, so it's really free, really open source, and we do not plan to make it commercial right now. So it doesn't have any commercial examples in the moment. Great. Good. Thank you very much for the questions. If you have more questions about this tool, we after we finish the talk, we have a small discussion round. So everybody who wants to want to talk with us or each other, and we can discuss a little bit about the tool or about other tinyML topics after we finished the rest of this talk. We want to thank our tinyML Foundation strategy partner, specifically our executive strategy partner, which are ARM, the powering tinyML innovations, then Edge Impulse, the leading edge ML platform, then Qualcomm advancing AI research to make efficient AI ubiquitous, then Cynthia, the end-to-end deep learning solutions for tinyML and edge AI, then our big thank to our Platinum strategy partners, which are DeepLight, the fastest AI video analytics solution on ARM CPUs, then ClickerTech, the global IoT solutions, LLT AI are pre-built edge AI sensing models plus tools for building your own. Then Winesys, a broad and scalable edge computing portfolio. A big thank to our gold strategy partners, which are Fedora Hub, Maxim Integrated, enabling edge intelligence, then Latent AI, adaptive AI for the intelligent edge, Micro AI, NXP, Seed, the IoT hardware enabler, SensiML, which builds smart IoT sensors derived from data, and ST and SynSense builds sensing influence hardware for ultra-low power embedded mobile and edge devices. A big thank to the end to our silver strategy partner, which are On-Device, EMSA, Greenwaves, Gravity, HOTG, ImageRevop, and Temuris, Fuses, Quexo, Wizos, SAP, and StreamNLS. Our next talk will be on Thursday, the 7th April, from Lucas, the CTO of Contact.io, and David, about battery optimization, people counting using FER and AI. Yes, thank you everybody for that you attendee our talk. Yeah, have a good evening, and if you want, you can stay and talk, and then we can have a small discussion about tinyML, about the topics if you have more questions, or yeah, everything about the tinyML field. Thank you very much.
Thank you very much.